Introduction to clock signal in digital circuits. First, let's define the clock signal. A clock signal is a periodic electrical signal that oscillates between high and low states. Clock signals are the heartbeat of digital circuits. They synchronize the operations in digital circuits, ensuring that data is processed and transferred at the right time. Clock signal characteristics. To define a clock, we need to provide the following information: clock source, clock period, duty cycle, and edge times. First, the clock source. The clock source is where the clock signal originates. It can be a port of the design or be a pin of a cell inside the design. It is usually generated by a crystal oscillator, phase-locked loops, which known by PLLs, or external clocks in some systems. Second, the clock period. The period is the time it takes for one complete cycle of the clock. It indicates time after which a clock will repeat its behavior. As shown in figure, the clock period is the time T for a complete cycle. This brings us to another important aspect of clocks, which is the clock frequency. The frequency is the number of cycles per second, measured in hertz. So the frequency of a clock signal determines how often it switches between high and low states. Higher frequencies result in faster operation of your digital circuit. If the period of clock is T, then its frequency F is defined as F equals 1 over T. Now let's see duty cycle. Duty cycle is the percentage ratio of the time the signal is high to the total time of one cycle. So, as shown in figure, the duty cycle is the ratio between the high time to the total period, T. Let's see some examples. Here, the high time is equal to half the clock period. So, the duty cycle equals 50%. And as shown in this example, the duty cycle equals 70%. Now, let's look at the fourth characteristic of a clock signal, which is the edge times. Edge times are the times for the rising edge and the falling edge of the clock signal. As shown, positive edge is when a clock transitions from state 0 to state 1. And negative edge is when a clock transitions from state 1 to state 0. Note: most complex designs require more than one clock for its functioning. When there are multiple clocks in a design, they would need to interact or share a relationship. This relationship can be synchronous or asynchronous. So, what is synchronous versus asynchronous clock signals? Synchronous clocks typically share a fixed phase relationship, as they are often derived from the same source. But asynchronous clocks are clock signals that don't share a fixed phase relationship. Having only asynchronous clocks in the design makes it really hard to meet setup and hold requirements when multiple clock domains are interacting. Let's define a type of clock signal known as the virtual clock. Virtual clocks are clocks that don't physically exist in the specific block, but represent an external trigger that impacts the timing of the block. A virtual clock has no source specified. In reality, it might have a source, but that source could be outside the block being constrained. We will have a question here: why we need to use virtual clock? Let me explain to you. In some cases, the user needs to constrain ports or pins in a block that has no clocks. In such cases, ports or pins are assumed to be triggered by or dependent on clocks outside the block. To capture the characteristics of such off-block or off-chip clocks, designers use the concept of virtual clocks. So to summarize, a virtual clock is a clock that exists but is not associated with any pin or port of the design. It is used as a reference in STA analysis to specify input and output delays relative to a clock. I hope you found this video helpful. Stay tuned for upcoming videos where we'll explore more topics related to IC design.